So the things we will discuss, first we will go through the LM function, which is the function in R that will fit a linear model. We'll solve an example, and we're making it interesting, so we're solving an example on ice cream. So it's basically ice cream consumption versus the temperature, and we're going to see if there's a relationship between the temperature and the ice cream consumption. And we're also going to solve the manually solved example that we solved in the last video manually. We're going to implement it in R and see if we get the same results. So without further ado, let's open RStudio and get the R code going. So if you open RStudio, you won't need to actually load any packages for using the linear model function or the linear regression function. I'm loading the library ggplot just because I like to visualize things with ggplot, but you can visualize things also with the base R functions. There are a few videos in the channel also about ggplot and how to utilize it. So let's go ahead and start. So for the ice cream, we're actually using a package in R that includes a lot of data sets. If you don't have it, you might want to install the package ec.dat, and the way to do it is just by this command, install packages ec.dat, and once it's installed, you just load the library, and once you load the library, all the data sets within that library would be available for you. So ice cream here is a data set in the ec.dat library. I'm transforming it to a variable I'm calling data, which is a data frame. So once you took it here, you can learn more about the data set by typing question mark and the name of the data set. It will tell you it's about the ice cream consumption, it's 30 observations, it's from the country United States, and it will explain every variable in that data. So let's do some exploratory analysis about the data. First, let's view the data set we have. So it does have 30 observations. Every observation has 4 variables. One outcome variable, in our case, is the consumption, and 3 other variables. Our interest today lies mainly in the temperature. So we want to see how the consumption, I think it's in pints, is related to the temperature in Fahrenheit. So first of all, let's look at the distribution of the consumption to understand the values that we are looking at in terms of the consumption. So we are doing a histogram here. So basically it's a ggplot. We pass the data itself. We tell it what are the x values, and we say it's a histogram, and we put our color and fill and the number of bins we would like. So here we can see the distribution of the consumption. We can see that there are some values of the consumptions that are outside the regular values. So we have some little amount of values that are reaching, I guess, 0.6 in this case, and most of our values are around 0.4. We can also look at the distribution of the temperature by the same way. So our x in this case is the temperature, and we are looking at the histogram. So this is giving us the temperatures that are within our 30 observations in 10 bins. So most of our temperatures are around 70, and we have some temperatures also on the low side. And in the middle side, the middle section, we have little observations. So this gives us an idea of the 2 variables that we are looking at. A more interesting plot in the case of regression is the scatter plot. So we want our x to be the temperature and our y to be the consumption. And we are going to plot it as geom point. So our geometric shape is going to be the points themselves. So we're going to see the scatter plot of the consumption in pints versus the temperature in Fahrenheit. And we can suspect from this graph that there could be some linear relationship. It looks like there is an increase with the consumption as the temperature is increasing, but we need to investigate this more. So one important thing to understand is the correlation. So the correlation is basically the relationship of one variable to the other. So as one variable changes, is the other variable changing linearly or not? And in the case of one variable, it's very closely related to the regression. So to do the correlation, you can just do core and put the data, and it would give you a correlation matrix of every variable in your data. But I like to use library core plot. So if you don't have it, you might want to install the package. It just gives you a visual representation of this correlation. So you pass to it the correlation matrix of your data, and you tell it upper, because the correlation matrix is symmetric. So whatever we have here, we're going to have in the other side. So we just take the upper part. And of course, the correlation of any variable with itself is 1. and hence we see these dark blue circles on the diagonal. But we're interested in the other values, and specifically we're interested in temperature. And as you see here, it's given us a shade that is probably around 0.8 or somewhere between 0.6 and 0.8. So it's telling us that there is a strong linear correlation between consumption and temperature. And this is promising for us because we are trying to do a linear regression between consumption and temperature. So now let's actually look at the number itself. So it's actually 0.77 or 0.78. So it's very close to the 0.8. So there is a strong correlation, which is kind of inferring that there is a relationship between those two variables. Now let's fit it with the LM function, which is in base R. So this is the function you would need for linear models. If we understand this function a little more, it takes as its arguments the formula itself. So you would tell it what is the outcome variable and what is the input, or the what are the covariates or the independent variables, and you would pass your data. And these two are the most important arguments. There are a few other arguments that you can look at. For example, if it faces a not available values, what should it do, and so on. But for us, now we're fitting an icecream.lm, and we're calling it icecream.linearModel, and we're using the lm function. We're passing the formula, which is the consumption, and you put this tilde, and you tell it the explanatory variable is the temperature, and you can take those two variables from the data frame called data. So just with this one click and one command, we fitted a linear regression model. And now we can look into the summary object of this model. So with this summary command, it would return to us all the summary about our linear model. So it gives us first the formula, so it's the consumption and the temperature. It gives us the residuals, and we will talk about the residuals a little more in another video, but basically think about them as the errors in our regression model. And it gives us, of course, the most important part, which is the coefficients. So if you remember from the previous video, our coefficients are the intercept and the beta, what we called in the previous video beta, which is the coefficient associated with our explanatory variables. And the summary object also tells us the significance level. So by seeing these stars, and significance is specifically important for the coefficient associated with the independent variable, because it tells us that this independent variable is a significant predictor of the outcome variable. So in our case here, the temperature is a significant predictor of consumption at a significance level less than 0.1%. So usually in statistical hypothesis testing, we're looking at significance level of 5%. So ours is way more significant than that. So we can say confidently that temperature is a significant predictor of consumption. So basically you can pull these coefficients. So you can pull the alpha value by calling it from the object itself. So icecream.lm is our linear model object. We just put a $sign and say give me coefficients 1, and the coefficient 1 is the alpha, and coefficient 2 is my slope or the beta. So if you have multiple variables, you would have more coefficients. So alpha and beta are equal to these values. So now I can easily understand the equation of the line that I'm looking at. So it's going to be alpha plus beta hat, of course, times the temperature plus the error. And if I'm interested in the expected value, which is the line itself, it's going to be the intercept plus the slope multiplied by the temperature. And now I can actually go ahead and look at the fitted values also from the object itself. So if I go ahead and make a plot similar to the scatter plot, but add to it a geom_point command that has icecream lm fitted values. So these are the fitted values for the 30 observations. So basically it's taking the 30 values of x that we have in our observations and calculating the yi hat for these values, which is different from the observed value. So these are the values that are actually on the line of our prediction. And to have the line itself, you just have a plus geom_smooth. So a plus geom_smooth here with method linear model, and I have the standard error as false because I don't want the shade of the error itself, because we still haven't discussed the error. And I just have the title, the labels for the x-axis and the label for the y-axis. So let's look at this. So now basically it's showing us the linear regression line, and it's showing us the fitted values in salmon, and they are actually fitted on the line itself, and they represent the yi hat for the observation I have. And this distance is the error of my predictions, which is the difference from the observed value and the predicted value. And this line, the beauty of this line is now I can forecast the average value or the expected value of a consumption when my temperature is 50, when my temperature is 59, which are values I didn't have before. If you remember from the histogram, we didn't have values in the middle side, many values, so we can predict what are these values. I can also forecast the trend, so I can see that as my temperature increases, my sales are gonna increase, and it's just basically with that same slope. Usually, however, I don't try to predict values outside my boundary. I can talk about the expected trend, but preferably we talk about values within the boundary of the regression line. So now we might be asking ourselves, perfect, we fitted a nice line that gives us some predictive values, but how much of the variability within the consumption is explained by the temperature? And this is given by the R-squared value. So if you look at here, it says the multiple R-squared. So basically it's saying that 0.6 or 0.6016 of the variability in consumption is explained by temperature. So we can say that 60% of my change in consumption is explained by the temperature, and there is something else going on that is affecting the other 40% of the variability. But now let's think about this. So we remember when we looked at the correlation plot, there was some tan value for the price itself. So it kind of says that when price is increasing, the consumption might be going down. So let's say, what if we add price to our model? And the way to do this is just to have a plus in your formula, plus price. So in this case, you're going to have an intercept, a coefficient associated with temperature, and a coefficient associated with price. If we fit this model, which is the LM.2 model, and look at its summary, we first note that the coefficients, yes, it's true, price is negative. However, we don't see these stars, which tell us actually that the p-value is not significant at a significance level of 5%, which is what we would be looking at or looking for. So we can say that price is not a significant predictor for consumption given a model that has temperature. So what about the interaction? So here we added them, but what about a situation where price and temperature are actually related to each other and they change with each other? It might not make sense with this type of variable, but for some other covariates that we might be using in actual real-life problem, there could be some interaction between the variables. And the way to think about the interaction is an additional term that is for temperature times price. So for this model over here, we changed this plus sign to multiplication sign. So we will have 4 coefficients. One is the intercept, one is the coefficient for temperature, and one is coefficient for price. And the fourth is the coefficient for the interaction term between price and temperature. So if we fit this and take the summary, we see that it gives us 4 coefficients, the intercept, the temperature, the price, and the temperature price interaction term. But we see that none of these are significant. So it tells us that this model is not good to predict the consumption. So we can discard this model, and we can discard the model that included price and focus only on one model that had consumption versus the temperature. So now that we are done with the ice cream example, let's go into the example of our data set that we solved manually in the previous video. So if you remember from the previous episode, this was our data and this is how it looked like. Basically, we had values of 7 observations, values of x and values of y. So if we manually build these into R, so we're going to say x equals a vector of 1, 2, 3, 4 until 7, and y is a vector that includes the values of y, and each of them is of length 7. Now, since my x and y include all the data, I don't have to pass the data anymore. So I will just say it's a linear model between y and the explanatory variable is x. And I'm going to fit it as example2.lm. So once I do, now let me look at the coefficients in the summary. First of all, we notice that the x is a significant predictor, and my coefficients are minus 0.28571 and 2.125. Now let's look at what we got when we solved it manually by hand. And in fact, when we solved it manually by hand, we got a minus 0.29 for the intercept and a beta of 2.25, which is exactly what we are getting with solving it with the R function. So the final step is just to view it again like what we did before. So we're passing the x values, we're passing the y values, and we're passing the fitted values, and we're putting the LM or the linear regression line into the graph. So we're ending with actually a graph similar to the one we have seen when we did it by hand, which has an intercept is going to go down over here until it reaches the 0, and it's going to be a minus 0.29, and it has a slope of 2.125. And as you see, it's very close to the point, so the errors are relatively small. And if we look at the variability explained, we can see that the variability explained is about 99.3% of the variability in y is explained by x. And in fact, we see that the line looks very similar to this line except for the scale itself, and it has the same equation as the line we got when we solved it manually. So with this, we complete our video for today. You have learned how to do linear regression in R, and there is an endless number of problems that you can solve with this very simple statistical model, and you would know if your predictors are significant. To download data, you can go into our video that gives you a few ways to download great data sets that you can start analyzing. And finally, if you like the video, please hit like, subscribe, and share it with others so they can benefit from what we are learning. And good luck with your data analysis.